So we say let Pn be the statement to prove. So I don't want to repeat the statement. I'll say let it be statement to prove, and this is the statement to prove. So basically this is Pn. Okay? So P1 will be when n is 1, P2 will be when n is 2. Yeah? So P1 will be n 1 cube, right? Plus 2, 1, which equals what? 3. And that is 3 into 1, right? So which means it's divisible by, so we can say, so P1 is true. Okay? I've just checked P2. Like I said, you don't need to check P2. Okay? P2, Nakita, do you remember the process that I put on the board? So we check for P1. We don't have to check for P2. Then you assume PK. What do we call PK, everybody? There's a word before that. The inductive hypothesis. Good. So P2, so we assume PK, then you have to use PK to prove K plus 1. And that is where the generalization comes from. Okay? So P2 will be 2 cubed plus 2, 2, which is 8 plus 4, which is 12, and that is 3 and some integer. Right? So we can say, so P2 is also true. Of course, you don't have to do P2 like I said once again. Now we assume PK is true. This is our inductive hypothesis. We will assume that PK is true. What does that mean? That means that K cubed plus 2K is divisible by 3. And that means that K cubed plus 2K can be written as 3m for some m which is an integer. Okay? And so usually when I'm doing this, okay, listen, when I'm doing this, I want to leave 1 or 2 lines here. You know why? When I want to substitute back.
Oh, because you need to change it.
So I can just include that, okay? So usually I would do that. So now we prove for n equals k plus 1, right? And what does that mean? We want to show that that's p k plus 1, k, what's that? K plus 1 cube, yes? Plus 2 k plus 1 is divisible by 5. Or I put it this way. It's divisible by 3. So equals 3 and some maybe r, where r is an integer. That's what we want to establish. Okay? So we start with what to prove. And we use this. So we have k plus 1 cube plus 2k plus 2k plus 1 actually. Okay, so what can we do? We want to make sure this is 3. So this is k cubed. This is 2k and some 3. Maybe we can open this bracket and see. Yeah? But at the end of the day, I'm looking at it this way. Actually, this is 2k. Actually, this is 2k. There are 2 things coming to my mind. If we make 2k the subject here, yeah, let's try it. If we make 2k the subject, 2k is 3m minus k cubed, right? Right? Then we can factorize, we can expand that. And the k cube will come out of it. So this is what I mean by that. So this is going to be, what is the expansion of this? Binomial. K cubed, 3k squared, 3k plus 1. Do you agree? This is 2k plus 1. No, plus 2. Does everybody get that? But we have something for 2k already. Okay? Now this 1 plus 2, I think the result is obvious already now. I can see it. I don't know if anyone has seen it. Has anyone seen how we can get 3 out of this? 2k, we bring this in. K cube, we cancel k cube. The rest of it have 3 as a common factor.
Oh.
Can you see that? So it's not that complicated. Can you see what I mean?
Wait.
So
2k
let's see.
equals
Okay.
3.
Let's write this one more step.
Oh, 2k equals 3 and minus k.
K squared, 3k. This is 3 and this is 2k. Can you see that?
Yes.
So this 2k is now going to become
Minus
3m minus k cubed. Can you see that? So this is k cubed, this is 3k squared, this is 3k, this is plus 3. What does that tell you? This cancels this, the rest can bring 3 out. And that is the r we are talking about, whatever that is left.
Yes.
Okay, so this is going to be 3k squared plus 3k plus 3 plus 3m, right? And that is 3k squared plus 3k plus
k.
or let's say, yeah. What? Oh, okay. Plus k plus 1 plus m. Now, is this an integer?
Yes.
K is an integer, m is an integer, then this bracket is an integer. So, indeed, the k plus 1 term is also true. P of k plus 1 is also true. And that's all we want to show. So, it's not really that complicated. You can see. So, that's why I always need like maybe a line here so that I can show, I can write what we need to substitute. Okay? So I'm just going to conclude by saying, since k squared plus k plus 1 plus m belongs to z, then p into k plus 1 is also true. Okay? And the conclusion will be, therefore, Pn is true for all n. Instead of saying that, you could say, yeah, you could repeat the instruction, the question again. Any questions? I want you to try this. It's a past IB paper. We'll do practice and correction, basically. Like, we'll do a lot of practice and correction in crowd. Prove that two n plus 1 is greater than n squared for all n in Z, n greater than or equal to 3. It's a past IB question paper. Is 7 marks altogether. Sweet. Should be very sweet. I think we can pause that because of the battery.